continuation to my previous class on single variable unconstrained optimization, today I am going into advanced to it, that is multivariable unconstrained optimization. Here we are dealing the optimization problems where the problems are of unconstrained type, but the objective function that is nonlinear in nature, but which involves more than one variables together. Now, we need to optimize the function after that. Now, for solving this kind of unconstrained multivariate nonlinear programming problem, there are several methodologies available, but that is a multidimensional minimization method. But here you see, whenever we are considering any nonlinear function may be continuous, may be discontinuous in the domain of definition. When it is continuous, then our differential method, that is a classical optimization techniques, that is differentiation of function, that works well. But when the function is not continuous in nature, in that case that differential coefficient calculation fails, because there is discontinuity in the domain of definition. In that case, what we do, we adopt searching technique there. But as you have learned in single dimension nonlinear programming, whatever searching techniques you have learned, those are not really working here, because you might be understanding here we are dealing with the surface. If there is a function of two variables, then in one axis one variable, in other axis another variable, in the third dimension the function moves. That way we are getting a three dimensional picture. That is why instead of having the function in the curve nature, we get the surface. That is why once we are getting the surface, if we just try to implement the searching techniques you have learned for the single objective problem, those are not working. There is a separate set of methodologies available for multivariate nonlinear programming problem. All the methodologies can be categorized into two types. One is the direct search technique and another one is the descent method. Basically, direct search technique does not depend on the differentiation of the function, whereas the descent method is very much dependent on the differentiation of the function. That is why it is easily understandable. Descent methods are not applicable when the functions are discrete in nature. Now, I will start my classes with the direct search technique. I will give you some idea how really we are dealing with the direct search technique. Now, there are again different techniques available. One is the random search, grid search, grid walk, then pattern search, that is a Powell's method. There are a few methodologies like that. I will not cover all the methodologies in detail, but I will give you I will show you few methodologies how it is working for a multivariate nonlinear programming problem one by one. And in the descent method, there is another set of methodologies available, starting from that steepest descent or steepest ascent method, Newton method, Quasi-Newton method, etc. Now, today I am starting with the direct search technique, that is the most popular technique is the univariate search, that I will show you first. Now, here the random search technique, random search what it does, it just exhaustively searches the entire domain and it considers the points randomly within the domain to find out the minimum value. But how to generate the random points in the domain? We use the random number generator. Through the random number generator, we consider different points on the space. From there, we are finding out a list of functional values with us, and from there we are finding out the minimum or maximum according to our desire. But one thing is there, that as you know, I have already explained you in my initial classes, that function may have global minimum or maximum or local optimum. That is why all these searching techniques, whatever I will discuss now, these are not really very much efficient to find out the global optimal value. Not only that, there is a curse of dimensionality as well, because if the dimension of the problem increases, if the number of variables increases of a function, that is why you could understand finding out the random points from a space where n number of variables are moving in different directions, in different ranges, in different scales, and generating random numbers for those, that is really a difficult task. But how really searching techniques are working, I will give you some idea of it, and I am starting my class with the univariate search method. The popularity of this method is there because of the easy calculation, because whenever we are considering a multivariate nonlinear programming in the univariate search method, what we do, we consider one variable at a time, keeping other variables constant. Okay? That is why if there is a function f x y, what we do, we start from a point in the domain of definition of the function. After that, we just move one variable at a time, say x. I will see whether x in the right hand direction or in the left hand direction, in what direction function is increasing or decreasing. Once we could see that function is increasing in certain direction, if my desire is to find out the maximum of the function, I will move through that path. But on the other hand, if we see the function is decreasing in another side, then if we are desiring to find out the minimum of the function, we will move in that way. What is the advantage? Advantage is that if I change x and y together, there are infinite number of directions altogether within the space. But once I am changing one variable at a time, that is why my options are left only. I can move in the right or I can move in the left. Alright. That is the thing we are employing in the univariate search technique. That is why if I just see the basic algorithm for univariate search, we start with a starting point. One of the variables is held constant, say x, then the function is optimized with respect to the other variable, say y. I can do the other way, I can keep y as constant and I can change x as well. Then in the next, I will do the reverse process. Either I will make y as constant, I will just change the x, in that way I will just move and I will do repeated iterations there. And after that we will see that the method will converge, because somewhere we will get the local optimum value, there we will stop. That is the basic idea. Now, for doing that thing, I have taken one example. Just to see the example, we are trying to minimize f x y, where x square plus x into 1 minus y plus y square, and the function we need to find out the minimum value within the range minus 1 and 1. Now, if you see the pattern of the function is this one. I have drawn this pattern in the Mathematica. Okay. Now, x and y, z are all moving, and we could see that several minima occurs. Function is not really unimodal within the range. Whether the function is unimodal or not, it is very difficult to find out all the time. Okay. Now, if this is the thing, now how really we can find out the solution for this problem? We need to find out a local minimum. Now, if you are interested to find out the global minimum, then you have to repeat the process by starting from different points within the range. I can start from minus 1, because this is a whole square, alright. Now, the x is actually this is written, I should write x in changing from minus 1 to 1, y is changing from minus 1 to 1. That is why we are getting a square of it. I can start from minus 1 and minus 1, taking both an x and y. I can start from minus 1, I can start from 1, 1, I can start from 0, 0. From anywhere I can start. Depending on my starting position, convergence will be reached quickly or not, that depends on that, because in the search process if the local minimum is there very nearby to the my guess point, that is my starting point, then quickly we will reach to the optimal solution. Otherwise, I need to find out, I have to repeat the process by starting from different guess points, and we will have a list of local optimum, and from there we can select the global optimum, that is there. But I will show you now how to reach to a local optimal point for this function at least. Alright. Now, let me start the process. Now, you just see this is my function x square alright. Now, my starting point is 0 0. This is my first point, alright. Now, if I start from 0 0, this is x, this is y. I can keep x as a constant, I can change y, or I can keep y as a constant, I can change x, alright. If I change x keeping y as constant, what is happening, you see, x is, this is the, now if x is, I am starting from x equal to 0, I can move this way or I can move that way. I will see if I move this way, what is the functional value, whether the functional value is increasing or not, and if I just move this way, what is the functional value increasing or not. I have to see that one. That is why you see there are two things are involved. One thing is that the search direction, in which direction I will do the searching, and the second thing is that what is the step length of searching. Shall I jump a lot or shall I move very with a small delta delta? That is why two things are involved here, search direction and the step length. You see, I have considered the search direction 1 0, alright, and let me consider a step length, that is 0.01, alright. If we just do that, we see that the functional values at f.010, that means my search direction was 1 0, alright, and my step length, say this is, here I have considered epsilon. Now, this is taken as a 0.01. Then if I find out the functional value at 0.010, that means I am moving from here to 0.01 only, alright. By keeping y as constant 0, we could see the functional value is 0.0101, alright. And what is the functional value at 0 0? That was 0 only. That is why functional value is increasing in the right hand side. Now you just take the reverse process. Now, the reverse is that instead of going this way, I am going the other way. That is why my search direction is -1 0, alright. Now, again I am taking the step length in the left direction as 0.01, then my point would be -010, alright. I am seeing, and again the functional value. What is the change in the functional value? If I just look at the values, we could see that functional value is increasing in the right and decreasing in the left. That is why what should be my desired direction? My desired direction always will be in the left, because I am searching for the minimum of a function, alright. But still you see, we have taken the probe length rather the step length initially as 0.01. That should not be, because step length I have taken in an ad hoc way. We should have certain mathematical logic how much step length we should take, so that quickly we can reach to the optimal solution. Okay. It may happen instead of 0.01, if I could have taken 0.02, then we could reach in the same way, the functional pattern is being maintained through that. That is why whether to take 0.01 or 0.2, there is a guideline to it. That is why I am saying that I am moving in the left is with a step length lambda 1, what it is, which is variable, all right. Then I can say, let me find it out the functional value as minus lambda 2 lambda 1 0, all right. That means my search direction is minus 1 0. I have seen the functional value is decreasing in that direction, and step length I have considered as a variable, that is lambda 1. Since it is in the left direction, I am considering f of minus lambda 1 0. If I just substitute here, what I am getting? Lambda 1 square minus lambda, all right. Now, what is my aim? My aim is to find out that obtain lambda 1 which optimizes f, all right. That means the first order derivative of f with respect to lambda 1 must be 0. What we do? We will consider df by d lambda 1. This is coming as 2 lambda minus 1 is equal to 0. If I consider this, we are getting lambda 1 is equal to 0.5. That is why it is clear that from this point I will move to the next point as minus 0.50. That is why I am starting from x1 0 0, I am moving here. This is my next point x2, all right. If I want to explain this one in the 2-dimensional space, just to see what is happening. This is the x, this is the y direction, all right. My range is from minus 1, 1, 1, minus 1, all right. What we did? We started from here, we checked everything, and we could see that if I just jump to the next, this point, which point is this point is minus 0.50, then my searching would be optimum, all right. Now, after reaching here, what I will do, as I said that in the last iteration we took x as a x as a variable, y as a constant. Here we are doing the reverse. We are considering y as a variable, x as a constant. Okay. If we keep x as a constant, what is happening? You see, we can move. If I just change the y, either we can move this way or we can move this way. Is it not? All right. Because I kept x as a constant. If I move this way, what is my search direction? My search direction would be 0, 1, all right. This is the S2, and if I move the reverse way, then it would be minus 0, minus 1. Let me see again whether the functional value is increasing or decreasing. We could see that if I move this in this direction, that means with a small probe length, epsilon is equal to 0.01 again. Again, I am not doing any optimization here to find out what should be the optimum step length, so that I could reach the solution very quickly. That part if I even do not do, if I just consider a small shift of y 0.01, then my initial point was x2, where I am reaching, that was minus 0.50, then here my point would be minus 0.5 plus 0.1, all right. I will see the functional value here, and I will see another in the lower part, minus 0.5 minus 0.01, all right. If we just calculate the values, I have seen this value is lesser than this. That is why it is we are sure that this direction is the best direction to get the minimum. This is not clear. Again the problem comes, if this is so, again the problem comes, okay, I am not moving this way, I am moving this way, from here to here I am moving, but what would be the optimal step length? That is again the question comes. Let me consider the optimum step length as lambda 2 in this case. Lambda 2 if I consider as a variable, then in the next what we will do? We will find out the point x 3 which is equal to x 2 minus lambda 2 s 2, alright, because if s 2, if I am going in the positive direction, it should be x 2 plus lambda 2 s 2, but here we are considering the negative direction, that is why x 2 minus lambda 2 s 2, alright. Now, in this point, what is the point is coming? If I consider this is minus 0.50, this is the direction is 0 minus 1, that is why 0 minus lambda 2, alright. If I consider this point is coming, I cannot take both as a minus, that is why if I consider minus here, I should take plus here, alright, minus lambda 2. Now, let me find out the functional value at x 3, that is a function of function of lambda 2 rather. Then what would be the function? I will get the function x square plus x into 1 minus y plus y square. Okay. Again I am doing the first order derivative and I am equating to 0. What we are getting? We are getting minus 0.5 plus 2 lambda 2 is equal to 0, which implies lambda 2 is equal to 0.5 by 2, that is equal to 0.25. Clear? Now, if we just move in this way, then what should be my x 3 in the next? If I just write down, then my initial guess was 0 0, my next point was minus 0.50, my next point is coming minus 0.5 minus 0.25, alright. Now, let us see the functional value at this point. These are the functional value as I was saying to you, and we could see the functional value at x 3 is coming as minus 0.3125, but previously the functional value was, it was 0, it must be more than that, that was 0.0099 like that, and now we are getting much better value. Okay. Now, the question comes, we can stop the process here, but we can move further even. How to move further? Again I will keep x as a variable, y constant, I will move this way. Okay. But it may happen if this is a local minimum and if my step length is very small, I will see after this functional value will never decrease. Functional value will increase in the neighborhood of this point. This is that is why we can declare that is a minimum. That is why question comes whether this point is at all a minimum or not, local minimum or not. But there is other method as well. I have checked with the grid search technique that this method gives us the global minimum. Not only there are several local minimums with the same values, but this is as well the global minimum. But how really you can sense it when you will do the mathematical process? That time you will see that if I go in the right direction or left direction, we will see there won't be any improvement of functional value. That means there won't be any possibility to get any minimum value than this. We have to stop the process, but we cannot. But this is one of the univariate search method, you must have seen. This is a very easy method, but there is another method that is mathematically very easy, but very difficult if you just do the calculations on your own. That is called the grid search method. I am just going to tell you that grid search technique now. Now, this is my domain of definition. I am getting, this is the, I am searching minimum within this range. This is my minus 1 0, 1 0, 0 1, 0 minus 1. Okay. What I can do? I can, in the grid search technique, what we do, we just divide the whole space in different with the grid points. How really? Let me consider that I am taking this 1.5, I am taking the grid point like this. Here also the same thing, minus 0.25, minus 0.5, minus 0.75. I can do the, I can take the grids like this. Alright. Similarly, I can take the grid points along y axis by considering the same way, minus plus 0.25, plus 0.5, plus 0.75, minus 0.25, minus 0.5, minus 0.75. Okay. Now, function is moving here as I showed you the picture. What I will do? I will find out the functional value at each grid point. For finding out the functional value at each grid point will not be difficult for you, because you can write a simple program for it. First you find out, you just divide, partition the whole space with different points, and you just see what is the pattern of the function there. How many points you will get here? You will get total here the 9, here 9. That means you are getting the 9 square points when we are considering 2 dimension. When we are considering 3 dimension, it will become 9 cube. If you have 4 variable, 9 to the power 4. That is why you can understand, if the number of variables are increasing, though we could guess what is the pattern of the function, but still finding out the functional value is really difficult here. For this problem, I found out few values of this. In that way, you can find out 81 points and functional value at 81 points, and you could see how the functional values are just moving here. Now, that way very nicely you can find out the local minimum, or if you want you can find out the global minimum. In the next class, I will continue my class with the same topic. Thank you for today.